All right, kids, here are your review solutions. So number one asks which are exothermic, one is combustion, two is neutralization, three is a bond between bromines, so that's endothermic. So the answer is A. For number two, which is true for a chemical reaction in which the products have more energy than the reaction. So remember, if we have reactions, products, if there's more energy at the end, it must have been gained. If it was gained, it's endothermic, and for an endothermic reaction, delta H is positive. Number three is a toughie. It requires a little bit of critical thinking. So it says you have 100 cubic centimeters of 1 molar HCl and 100 cubic centimeters of 1 molar NaOH. When we mix them together, the temperature of the solution increases by 5 degrees Celsius. What will be the temperature change when 50 cubic centimeters of these are mixed? So the amount of heat that's released is dependent upon the mass of the substance, right? MC delta T. So if we have 200 total cubic centimeters here, we would have 50 total cubic centimeters there. So you're gonna, with the 50 cubic centimeters, you're gonna release half as much heat, but they also have half as much mass, so the temperature change will be the same. The answer is B. I'm recording a video, please wait. How much energy in joules is required to increase the temperature of 2 grams of aluminum from 25 to 30? The specific heat is 0.9. So this is just plug, chug, and solve. Mass is 2. Specific heat is 0.9. Temperature change was 5 degrees, so 10 times 0.9 is 9. All right, using the equation below, what's delta H for the following reaction? So this is Hess's law. First thing I see is MnO2. In my step, it's on the wrong side, so if I call this one A and this one B, when I'm calculating delta H, the first thing I'm going to do is negate B. Next thing I see is carbon. Well, carbon is, there's 1 mole on the reactant side. Here there's 1 mole on the reactant side, so we're just going to add A. When we substitute the numbers, it's going to be negative B, which will be positive 520, plus A, which is negative 394, so minus 394, when you do this math, you get positive 126. Which process represents the carbon-chlorine bond enthalpy in tetrachloromethane? So remember, bond enthalpy is the energy change, or the energy that is needed to break 1 mole of bonds in the gaseous phase. So if it's 1 mole of bonds, carbon tetrachloride has 4 moles of carbon-chlorine bonds. So one of them broken would leave CCl3 and Cl. Oh, you can't see, darn it. I couldn't make the video yesterday because somebody interrupted me when I was in the middle of recording. And the same thing happened now, but I'm just going to power through. All right, so what is the energy in kilojoules when 1 mole of carbon monoxide is burned according to the following equation? Well, the equation tells me that for every 2 moles of carbon monoxide, I release 564 kilojoules of energy, so half the number of moles would release half the amount of energy. All right, number 9, 1 gram of sodium hydroxide was added to 99 grams of water. The temperature of the solution increased from 18 to 25. The specific heat capacity of the solution is 4.18, which expression gives the heat evolved in kilojoules per mole. All right, so obviously this is going to be our equation, negative Q. Ow, something happened with the nerves in my hand. Negative Q over N. So we're going to have MC delta T in the numerator. So I should expect to see in the numerator 100, they combine the mass in the old curriculum, times the specific heat, which is 4.18, times the change in temperature, which were 18 to 20.5, so it's 2.5. I almost reached for my calculator. Now, if we're going to divide by the number of moles of sodium hydroxide, to get moles, we take the mass and divide by the molar mass. So up here I should have the 1 gram is included in the 100, excuse me, but then I have to divide by the molar mass, which is 40. Now, that mass that I plugged in was a gram mass. And when you plug in grams, your answer will be in joules per mole. We're specifically asked for kilojoules, so I also have to divide by 1,000 to make that conversion, so the answer is B. Yes. All right, some water is heated using the heat produced by the combustion of magnesium. Which values do we need to calculate the enthalpy change? So again, enthalpy change will be that. So for Q, I'm going to need the mass of water, and I'm going to need the temperature change of water. And for the N factor, I'm going to need the mass of magnesium. So we're going to need all three. All right, which statement is correct given the enthalpy level diagram below? Well, this is for an exothermic reaction. So the products have less energy than the reactants, so they are more stable. So the reaction is exo, and the products are more stable than the reactants, yes. Which is correct about energy changes during bond breaking and formation? Well, it takes energy to break a bond, and energy is released when a bond forms. So bond breaking is endothermic, so those are out. And if it's endothermic, delta H must be positive, so the answer is C. Which processes are exothermic? Ice melting takes energy to melt ice, so no. Yes, we do know that those two are, so 2 and 3. Which equation represents the bond enthalpy for the HBr bond in hydrogen bromide? Well, first of all, bond enthalpy means everything is in the gas phase. So let me just check here. Oh, we got liquid over there, liquid over there. Okay, so if we break the HBr bond, what we're going to have is 1H and 1Br. This represents the breaking of this compound, but the formation of molecules. So the answer is A. Which statement about bond breaking is correct? We already did one just like this. Bond breaking is endothermic and requires energy. Considering the following reactions, so we got another Hess's law here. First thing I see is N2. In my step, it's correct. The coefficient is correct, and it's on the right side. So when I'm calculating delta H, I'm just going to add this value as it is. Next thing I see is O2, but it appears in 2 steps, so we'll skip it. Then I see NO2. Here I have 2 NO2 on the product side. In my step, I have 2 NO2 on the reactant side, so I got to flip that one. So I'm going to negate 112 and subtract. So it's going to be 180 minus 112, which looks like C. Now on to the short answer. So the data below are from an experiment to measure the enthalpy change for the reaction of aqueous copper 2 sulfate and zinc. So we got a volume and a concentration of copper 2 sulfate. Remember, that'll give us moles. I'm doing this before I even get into the problem because you know we're going to need it. So 50 cubic centimeters is 0.05 cubic decimeters. That means I have 0.05 moles of copper 2 sulfate in my solution. It was placed in a polystyrene cup, and zinc was added after 100 seconds. The temperature time data was taken. Data logging software program. Straight line, blah, blah, blah. Use the data presented by the software to deduce the temperature change which would have occurred if the reaction had taken place with no heat loss. So this is our extrapolation. We mixed our ingredients at 100. The temperature went up. So that mixture started losing heat the moment the temperature went above the room temperature. So to figure out what the temperature would have been, we just have to look at the rate of cooling and extrapolate back all the way to the point that we mixed the reactants together. So the temperature would have reached that point, which is 70 to approximately 73 Celsius. All right, so next it says calculate the heat produced during the reaction. It tells you the heat will be the volume of copper sulfate times the specific heat capacity times delta T. It wants it in kilojoules, so we have to make sure we plug in the kilogram amount. So if it's 50 cubic centimeters, that would be 0.05 cubic decimeters, which is 0.05 kilograms. So Q will be 0.05. You heard the bell. I'm going to have to let all the kids in. It might get a little chaotic, but I'm going to tell them to be quiet. All right, so 0.05 times the specific heat of water times the temperature change, which was 22 for about initially 25. Finally, 73, when you punch these numbers in, 0.05 times 4.18 times 23, not negative, minus 25 minus 73, I get negative 10 kilojoules. And we got, I don't really care about sig figs, negative 10 kilojoules. The color went from blue to clear. So deduce the amount in moles of zinc which reacted in the polystyrene cup. So if it went clear, it means all the copper was reacted, which means it was limiting. If we look at the equation, there's a 1-to-1 relationship between moles of copper 2 ions and zinc. If we started with 0.05 moles of copper 2, then we reacted 0.050 moles of zinc. So now I've got kilojoules, I got moles. I bet you $10 they're going to ask me to calculate delta H, and they do. So delta H is negative Q over N. So we have negative 10 kilojoules, so it's going to be 10 in the numerator and 0.05 moles in the denominator. So 10 divided by 0.05 equals 200 kilojoules per mole. All right, I'm going to pause the recording and let the kids in. Please. All right, so one important property of rocket fuel mixture is a large volume of gaseous products form which provide thrust. So hydrazine is used as rocket fuel. Here's an equation for it, and it gives us a delta H. Hydrazine reacts with fluorine to produce nitrogen and hydrogen fluoride, all in the gaseous state an equation. So it tells us hydrazine is N2H4, added to fluorine. I'm going to say it one more time. Please be quiet. I'm recording a video. Obviously, I'm doing that, so I need everybody to be 100% quiet, or I'm going to pause it and kick you all out. And now this is going to be on YouTube, so please be quiet. All right, so then we're going to produce hydrogen fluoride and nitrogen gas. So we got to go ahead and balance this. I got 2 nitrogen. I've got 2 fluorine here, so I got to do a 2 there. Oh, actually, I'm going to need a 4 there for the 4 hydrogen, which I need 2 on fluorine, and there we're balanced. Use the average bond enthalpies in table 11. I automatically know. Then if the next voice I hear, I'm kicking everybody out. In fact, I'm going to do this so that everybody who's in here knows I'm recording a video. Everybody else can be. Just, do you see why the job frustrates me? Okay, so when we're doing average bond enthalpy, the equation we use to calculate delta H is the sum of the enthalpies of all the bonds broken minus the sum of the enthalpies of all the bonds formed. So it's basically going to be reactants minus products. I'm just going to pull these values from the data booklet. So the first thing we're going to have is in hydrazine, we're going to have a bond between the 2 nitrogen atoms. So that'll be 1 nitrogen-nitrogen bond. And I have 4 total nitrogen-hydrogen bonds, so 4 times the nitrogen-hydrogen. I also have 2 fluorines, so 2 times the fluorine-fluorine bond. From that, we're going to subtract all the bonds in our reactants. Each HF has 1, and there's 4 of them, so 4 HF bonds and 1 mole of nitrogen triple bonds. Now I'm just going to substitute the numbers in. So close to being done. In fact, there's only one more. This is all right, so I'm just going to look them up. You can find them yourself. All right, so nitrogen is 158 plus 4 times the nitrogen-hydrogen, which is 391, plus 2 times the fluorine-fluorine, which is 159, and that's all of that, minus 4 times HF, which is 567, plus 1 times nitrogen triple, which is 945. Now we just got to punch this into our calculator and we'll be done. So 158 plus 4 times 391 plus 2 times 159 minus 4 times 567 plus 945. Presto changeo, I get negative 1,173 kilojoules per mole. All right, based on your answers to part A and C, suggest whether a mixture of hydrazine and fluorine is a better rocket fuel than a mixture of hydrazine and oxygen. So hydrazine and oxygen released that much energy per mole of nitrogen, and with fluorine, per mole of nitrogen, we release about double. So yes, fluorine is better. Also, in rockets, they eventually get to a part of the atmosphere where there is no oxygen, and oxygen is required for combustion. So hydrazine can actually combust without oxygen being present, which is nice. All right, last Hess's law. This one was in the multiple choice, so I'm going to skip it. All right, hopefully this video helps you to study for your test, and I'll see you guys on test day.